thanks for clicking. Welcome to another Narculus production. Today, we are going to be approximating the area that is underneath the curve. Okay? So we are going to be taking a look at functions, all right? And using those functions and taking a couple of bounds and approximating the area that's underneath that curve. So let me show you what it is that we're talking about trying to do here. So suppose you wanted to find the area that's underneath the curve. Now we're going to use f of x equals 5 minus x squared in just a minute. But let's just take any old function. It doesn't matter what it looks like. Let's just draw anything. So let's draw something called f of x. Here we go. Okay, here's f of x. I want to find the area, let's say from A over to B. The area under the curve is the area that's bounded by the curve and the x-axis. Okay, it's bounded by the curve and the x-axis. All right, so what I'm looking at is I want to find this area. How much is this? Now the problem is the issue you have, I guess, with area and finding area is that you know a lot of area formulas, but they're area formulas for certain shapes, right? That you know exactly what they look like. But when we draw functions, f of x, some kind of curve, well, those functions don't necessarily look like in any way, perhaps, those traditional shapes that you're used to, a triangle or a rectangle or a circle, okay? So you can't use any of those formulas. So the question is, how would you find the area that's underneath this curve without it? So what we're going to do here is we're going to find the area that's underneath the curve f of x equals 5 minus x squared. So here's 5 minus x squared. This is my function f of x. I want to find the area. We're going to look for the area between 0 and 2. So the area is all of this. This is the area that I want to calculate. Okay, that's what we're going to do on the next slide. Now, we want to find that area. So to find it, what we're going to do is we can't find the exact area that's underneath this thing because this is not a shape that you've seen before. You don't know the area formula for this. This parabola here, half a parabola, a piece of it. You don't know that area formula. So what we're going to do is we're going to approximate the area. It's the best we can do. And to start approximating areas, we're going to use rectangles. Okay? So we're going to use rectangles in this region to approximate the area that's underneath the curve. That's how we're going to start approximating the area. All right, now there's other ways you can do it as well, and some of those we will see in the future. But for now, we're going to work with rectangles. So let me show you how this is done. Okay, so again, what we're going to do is we're going to divide the area. So 5 minus x squared is what we're using. Let's come back and draw another picture of it real quick here. So we have 0 over to 2. And I'm going to try to draw it a little bit bigger so it's a little easier for everybody to see what it is we are doing. So here's my function f of x. And what I want to do is I want to approximate this area. Cut this off here. Okay. And again, just so you understand, this point, right, can't end up on the x-axis because if I plug 2 into f, 5 minus 2 squared is 1. So really this is 1 here. Okay, so I can't put this point on the x-axis. It would be nice if I could, but I can't. All right, but this is the area that I want to calculate. Okay. And what we're going to do is we're going to divide this region into rectangles of equal width. Okay. So we're going to divide up this from 0 to 2 into equal parts. So the first thing we're going to do is we're going to approximate the area underneath this function, 5 minus x squared, on the interval between 0 to 2, using what we call left endpoints or a left Riemann sum. We'll learn much more about Riemann coming up. And 4 rectangles of equal width. So it says they're supposed to be equal width. Okay, so the first thing we need to do is figure out how to divide up our x-axis. We want to make 4 rectangles of equal width. So to figure out what delta x would be, I'll do it over here. Delta x, we can write as b minus a over n. So b would be the 2 minus 0. So basically I have 2 units to work out on the x-axis, and then I want to divide it into 4 equal pieces. So 2 over 4 is 1/2, which means that I should make each mark a half a unit away. So starting from 0, I'll make a mark at a half. Then I'll go another half, I'm at 1. Then I'll go another half, I'm at 3 halves. And then I'm at 2. Okay? So now, what we're going to do is we're going to draw 4 rectangles in here. This is how we divided it up. So basically what we have is this, just so that you can see. We have 4 bases. Okay, you can see them. 1, 2, 3, 4. And we're going to use left endpoints or a left Riemann sum. That's extremely important because it's telling you which side to start from. So for example, I'm going to start from the left-hand side, from 0. Okay. What I'm going to do is I'm going to go up to this point on the curve, make a point there. So this distance is going to be my height. And then I'm going to draw across and down to the 1/2. This is rectangle number 1. Okay? It's extremely important that you know how to draw these. If you can draw it, you can do any question I ask you to do. Now I'm going to go over to a half, go up to the point that's on the curve, draw across to 1, and down. That's rectangle number 2. From 1, I'm going up to the curve, make a point, draw across and down. That's rectangle 3. And then finally, I'm going to go over to 3 halves, up to the curve, make a point, draw across and down. That's rectangle number 4. There's my 4 rectangles. Now, what's the advantage of this? Well, the advantage is I can find the area of a rectangle, right? The area of a rectangle is base times the height. So that's easy. It's an easy formula to work with. I know how to find the area of it. Obviously, this is not going to be the real area that's underneath this curve, right? I mean, literally, you can see it on the picture. The rectangle's area is going to be more than the actual area. And that's something we'll talk about coming up, okay, in a slide in a few minutes. So first thing, let's actually try to find the area of each of these rectangles. So let's try to find the area. So each area is the base times the height. Let's try to find the area of rectangle number 1. Okay, so the base of the rectangle is this distance. So the base of it is a half a unit. Now to calculate the height, or I could find the height, it's this point, right? Okay, or the height is just f of 0, right? Because this point is on the curve. That's why when we're drawing the rectangles, we're making sure that one point is on the curve because we can calculate that point because we know f of x is 5 minus x squared. So my first rectangle is going to have a base of a half, and its height is going to be calculated by finding f of 0 because that's how far it'll be from the bottom up to there. For rectangle number 2, my base is again 1/2 of a unit, from 1/2 over to 1. But to calculate the height, I'm going to calculate f of 1/2. That's how tall this thing gets. The third rectangle is going to be 1/2 times f of 1. And the fourth rectangle is going to be 1/2 times f of 3 halves. When you start from the left, the only function you don't evaluate, or point you don't evaluate at, is the far right point. Okay, we don't use that. You can see it's not on the curve, right? The rectangle, the height of the rectangle is not on the curve there. All right, so now we just have to do these calculations. So we have 1/2 times f of 0. F of 0 is 5, right? So that's 1/2 times 5. And then 1/2 times f of a half. So f of a half is 5 minus a fourth, which is 4 3/4. And I'm going to put that as an improper fraction, 19 over 4. Okay, so we got 19 over 4 there. And then 1/2 times f of 1. So f of 1 is 4. And 1/2 times f of 3/2. I'll come over to this side here. F of 3/2, that's 5 minus 3/2 squared is 9 over 4. And that's going to be 20 over 4 minus 9, 11 over 4. Times 11 over 4. Okay, let's multiply all 4 of these, and then we'll sort things out. So that's 5/2. That's 19 over 8. That's 2. And that's 11 over 8. All right. So now I want to find the area that's underneath the curve. Well, I want to approximate it. To approximate the area that's underneath the curve, what do I have to do with all 4 of these areas? Well, I got to add them together, right? I just add them, and that gives me the approximate area. All right, so I got to make all these 8s. So that's 20 over 8, 19 over 8, 16 over 8, and 11 over 8. All right, so these two make 30. 50 and 16 is 66 over 8. We could reduce that, or we could leave it 33 over 4, or you could write it as a mixed number if you want, 8 1/4. Any one of those is fine. Okay, that is the approximate area that's underneath the curve. Now, is this the true area that's underneath the curve? No. Okay, it's too much. Right? The area of this rectangle, these rectangles, add extra area that's not underneath the curve. So it's too much. It's an over approximation. All right. All right. That's how you draw left endpoints. Very important to know how to draw them. Okay. Because now I want you to approximate the area underneath the curve 5 minus x squared between 0 and 2 with 4 rectangles of equal width using right endpoints. So basically, we're going to repeat the same process, but now we are going to work from the right. All right, so we have to divide up our x-axis. We have 2 units to work with, so delta x is going to be b minus a over n. So that's 2 minus 0 over 4. So that's half a unit each. So we have 0. Next is a half. Next is 1. Next is 3/2. And finally, we have 2. Okay, we are going to work from the right. We're going to work from the right. That means we're starting from the far right point. So here's my base here. And then I'm going to go up to f of 2, up to the curve, draw across, and down. That's rectangle number 1. And then I'm going to go over to 3/2. Go up to the curve, make a point, draw across, and down. You can fill this in here. That's number 2. 1, up to the curve, draw across, and down. That's rectangle number 3. And then up to a half to the curve, draw across, and down. That's rectangle 4. Okay, there's my 4 rectangles. Now I need to calculate the area. Now, this is an approximation, right? It's not the true area. You can certainly see it's not enough. Okay, it's short, right? It's missing area that's underneath the curve. All right. We're finding the area of the rectangle, which is the base times the height. So we're finding the area, which is base times the height. Let's start with rectangle number 1. Rectangle number 1, its base is still a half a unit, and its height is f of 2. The second rectangle, the good news is some of these are repeats. 1/2 times f of 3/2. The third area is 1/2 times f of 1. And then the fourth area is 1/2 times f of a half. And now the only point we don't use when we work from the right is the far left-hand point, which was 0. Okay, now we got to calculate all these. The only one we really have to calculate, though, is f of 2, right? Because the other ones we already did on the previous slide, so we're going to go look back here real quick. So that's 1. So that's 1/2 times 1. And then we have 1/2 times f of 3/2. We did that on the previous slide. F of 3/2 was 1/2 times 11 over 4. 1/2 times 11 over 4. And 1, if I plug 1 in, I get 4, half of 4. And then if I plug 1/2 in, that's 1/2 times, I could just do it, 1/2, 5 minus 1/4, which is 4 3/4, 19 over 4. Okay, so now let's figure this out. We got 1/2, we got 11 over 8, 2, and 19 over 8. So let's see, let's turn these into 8s. So that would be 4 over 8, 11 over 8, 2 is 16 over 8, and 19 over 8. And we're going to add these 4 together and see what we get. So that's 20 and 30. So that's 50 over 8, which you can reduce to 25 over 4, which is 6 1/4. So the area underneath the curve using right endpoints is approximately 6 1/4. Okay? So the area of this function from 0 to 2 is approximately 6 1/4. Now, is that right? No, it's not enough. This is an underestimate. Okay? So that begs the question, right? Will the approximation be an underestimate or overestimate of the true curve if you didn't draw the picture? How could you figure that out? Well, we already know it's all about how you draw left and right endpoints. So here's 4 pictures. These 4 pictures, each one of them is either increasing or decreasing. It's concave down or concave up. So the question is, what makes the difference? So let's say you were going to draw from the left. Let's try to draw from the left. We'll start here. So if we're going to draw from the left, we're starting here. Put a point there, draw crossing down. Point there, crossing down. Point there, crossing down. Point there, crossing down. Point there, crossing down. So this is an underestimate when I draw from the left. Okay? What if I drew this from the left? Point here, crossing down. Point here, crossing down. Point there, crossing down. Point there, crossing down. So from the left, it's under. From the left, it's under. What about from the right? What about on this one over here? We draw from the left. Oops. Point here, crossing down. Point there, crossing down. Point there, crossing down. Point there, crossing down. Now it's over. The left is over. Here, the left is definitely over. Okay. What if I tried to draw from the right? So let's just take a second and kind of erase these. What if I wanted to draw from the right this time? Let's try from the right. From the right, crossing down, crossing down. From the right, it's over, this picture. Here, also over. Here, under. And over here, under again. So, using the information we've gathered here, what makes the determination as to whether or not the left and or right endpoints are underestimates or overestimates. Okay. What is it dependent on? It depends on, oops, I'm missing an H, whether F is increasing or decreasing. Right? It depends on whether F is an increasing function or a decreasing function. When F over here is increasing, it doesn't matter if it's concave up or concave down. If it's increasing, the lefts are under, the rights are over. When it's decreasing, the lefts are over and the rights are under. Okay? That's what makes the difference. That's what the determination is. All right? Okay, finally, this is what you're going to see often in this course. Not necessarily doing it with functions all the time, although you could. There's nothing wrong with it. Okay, but we tend not to. We tend to do it in charts. Here's a chart with x values and g of x. It wants you to find the area underneath the curve g on the interval 0, 10 using left endpoints. Okay, using left endpoints. And let's say 4 subintervals. Okay, 4 subintervals, 4 rectangles. Now, notice I didn't say equal width. Okay, and I'm going to show you why in just a second. So here's what we're going to do. All right, I am not going to draw this picture. I'm not going to put these 5 points on my graph necessarily, all 5 of them, and plot them and make f of x. All I'm going to do is this. Okay, I'm going to label the x-axis with the 5 values on the x-axis. 0, 3, 4, 8, 10. And this is the easiest way, I think, for you to do this, okay, until you get the hang of it, until you understand how the whole thing works. All right, I'm going to draw a curve. I don't care what the curve looks like. It doesn't look anything like those points, and I don't really care. I'm calling it g of x. And now what I want you to do is I want you to work from the left with 4 subintervals. Okay, now it doesn't say they have to be equal width. And you can actually see, if you look at these points on the x-axis, the widths are not going to be equal. 3, 1, 4, 2, they're not going to be equal. That's why it says they're not equal. I don't use delta x here, b minus a over n, because I can't divide them into equal widths. Okay, I have to use the widths that are given to me. All right, so left endpoint, starting from the left, draw across and down. That's rectangle 1. From the 3, across and down. That's 2. From the 4, that's rectangle 3. From 8, that's rectangle 4. So now I want to find the area of each one of these. How would I do that? The area of the first one is going to be the base is 3 units times g of 0. And I'll go in the chart in just a minute. Area number 2 would be 1 unit from 3 to 4, g of 3. Next area, 4 for the base, g of 4. And finally, 2 for the base, g of 8. So now I'm going to go into my chart. That's 3 times 5, 1 times 1, 4 times 6, 2 times 11. So that's 15, 1, 24, 22. Add them all up. So that's 16 and 24 make 40, 62. Okay, that's the area, 62. All right. So you can see what we did here. Basically, all I did was just draw some random picture, put the x values down here. Okay, they're not equal width. By the way, the reason why they're not equal width is because they don't have to be. They don't have to be. The person we credit with that is a man named Riemann. Okay, So a lot of times what we say is okay, use a left. This problem would usually be written as use a left Riemann sum to approximate the area underneath the curve. So they want you to start from the left. When they say Riemann sums, Riemann rectangles, you use rectangles. All right. Now let's do the same thing using right Riemann sums. Okay, again, 4 subintervals. And right Riemann sums, that means we're going to use rectangles. Okay, let's draw a picture here. So we have 0, 3, 4, 8, 10. Just draw anything. There it is. G of x. And now we're going to draw from the right 4 rectangles. So starting from the 10, put a point, crossing down. That's rectangle 1. Go up to 8, point, crossing down. That's 2. Over to 4, crossing down. That's 3. 3, crossing down. That's 4. And now to find the area of each one, the area of the first one will be 2 units for the base and g of 10 for the height. The second one is 4 units, g of 8. Then we have 1 unit, g of 4. And finally, we have 3 units, g of 3. So let's come back to our chart. 2 times g of 10, 7. 4 times 11. Then we have 1 times 6. And then we have 3 times 1. So that's 3, that's 6, 44, 14. These two make 50. And 17, 67. Okay, so again, this is an approximation. 67 is the value. And we worked from the right. Okay, so what's most important here from this video is that you understand how to draw from the left and from the right. Because if you can draw from the left and from the right, then the actual numeric calculations will be the easy part because you can see what you're going to have to write down for each base and what you're going to have to calculate to get the height. All right? So that's the most important thing here. You have to be able to draw and understand, how do I draw from the left versus how do I draw from the right? And when am I allowed to use delta x and when am I not? I can only use delta x, that formula, b minus a over n, if it says they're of equal width. If it doesn't say they're equal, you cannot use that delta x formula. You just have to use the values that have been given to you and just approximate it using those values that have been given. Okay? And that's it. And as always, thanks for clicking.